Hello students, welcome back. So now we are going to design a bidirectional shift register. So in this video, we are going to talk about that what are shift registers. We are going to discuss a parallel input, parallel output shift register, and we will discuss the feature of bidirectional shift. And then we are going to design it and implement. So first of all, when we talk about the shift registers, we had observed that serial input or serial output, whenever one of these combination is present, we need to shift the data because we can only load one bit at a time. That means the shifting is a must operation. The shift can be done in one direction as well as in both the directions. One bit is shifted at any given time. Whenever we deal with the shift in registers, we will always shift by one bit at a time. These kind of registers are mostly used in pipelining operations. So we are going to design a parallel input, parallel output bidirectional shift register. The specifications of this register design are that there should be 4 input bits and parallel data can be loaded. I need to have 4 output bits and parallel data should be accessible. 1 bit input on 2 sides, left as well as right, so that we can give the input for shifting as well. And we will have 4 different control cases. What are these cases? Let us discuss these. We are saying we need to perform one of the 4 operations, and these 4 operations are as follows. We can hold the data, keep the 4 bits as it is. We can left shift, we can right shift, and we can load a new data. At one given time, only one of these 4 will be performed. So therefore, we get the idea that if I have to perform 1 out of 4 operation, I can take 4x1 multiplexer with a D flip-flop and try to make this. So then we say, let us make the 1-bit version first. So here is the circuit diagram. So what we observe here, that we have a 4x1 multiplexer on the top. There are 2 select lines which are given the name CTRL, that means control. They are going to perform 4 different operations. They will help us in making the decision. When we keep the value of CTRL as 0, 0, then we will perform hold operation. For 0, 1, left shift. For 1, 0, right shift. And 1, 1 will be used for loading a new data. Now, if you have a look at this 1-bit circuit, you can see that the input of 0, 0 is attached to the output of D flip-flop. That means we are going to hold. When we are performing left shift, a new input is coming from left shift XL. When we are performing right shift, a new input is coming in the form of XR. And when we are loading a new data, then D is coming at 1, 1. Now let us extend it for a 4-bit version. So here I have a 4-bit bidirectional parallel in, parallel out shift register, and let us understand that how this circuit is going to work. Let us talk about the hold operation. There are 4 bits. So 0, 0, 0, 0, 0, 0 and 0, 0. All these 4 are connected to the respective outputs. So whenever I select CTRL as 0, 0, the same 4 bits will be back to the multiplexer and we will receive them at D. D0, D1, D2, D3. Now, if I select 0, 1, this is going to take a new input. And look here, this 0, 1 is coming from this bit. That means the value from this register will go to this register. Here 01 is connected to this one. That means the value will shift here. And this 01 is connected here. That means the value will shift here. So the complete data will be left shifted. For right shift, I will set CTRL as 10. A new bit will come here. This 10 is connected here. That means this will go here. This 10 is connected here. That means this value will be transferred here. This 10 is connected here. So we will transfer it this way. So all the bits will be right shifted. And when I set CTRL as 11, then we are going to take new bits D3, D2, D1 and D0 in all 4 places. So a new set of 4 bits will be loaded. So this is how we can design a 4-bit bidirectional parallel in, parallel out shift register. Now let us implement it using multiplexers and D flip-flops in Verilog. Now let us talk about the coding part. First of all, I have to declare a new D flip-flop which is having the support of clear signal as well. So inputs are D, clear, clock and Q. So I have very simple code. Always at the rate positive edge of the clock, begin and end. If clear is equal to 1, Q is 0. That is the purpose of clear signal. Else Q is equal to D. This is our normal D flip-flop. Now once we are done with that, we already have 4x1 multiplexer. So we just need to revisit and see that what is the sequence of my ports. And now I come to my main code. So here I have my ports. First of all, 4 bits of D, 2 bits of control signal. One is clear, one is clock, one is XL, one is XR and output is a 4-bit. So that is about the ports. Now comes the mapping part. I need to connect 4 different 4x1 multiplexers with 4 D flip-flops. So I need those 4 wires. So I have taken wire 3 to 0 and the name of wire is S. Now for the multiplexers, the first input is I0, I1, I2, I3. We will revisit the circuit diagram and see that where are I0, I1, I2 and I3 connected for the first multiplexer. We can see that I0 is connected to Q0. I1 is connected to XL. I2 is connected to Q1 and I3 is connected to D0. This is what we have to take care. So we have connected I0 to Q0, XL, Q1 and D0. These are 2 control lines and the output of multiplexer we are shifting to the wire S0. In the next multiplexer, I0 will be Q1, I1 will come from Q0, I2 will come from Q2 and then D1 is at I3. Same control line and next wire. Similarly, we write for the third multiplexer and when we come to the fourth, which is for MSB, I0 is Q3, I1 is coming from Q2, I3 is D3 and I2, which is right shift, will come as a new input XR. Same select lines, 3, 2, 1. Same select lines and S3 is our wire. Now we come to the D flip-flop. In the D flip-flop, the arrangement is simple. Let us just revisit the circuit first. In every D flip-flop, we can see that clock is common. Clear signal is also common. the input of every D flip-flop is coming from the wire S0, S1, S2, S3, and output of every D flip-flop is Q0, Q1, Q2, Q3. So here we have done the same. For the first D flip-flop, input is S0, output is Q0. Clear and clock, they are same for everyone, and S0 becomes S1, S2, S3, Q1, Q2, Q3 for 4 D flip-flops. This is our code. Now let us check the schematic. We can see the schematic that D is going at I3 of every multiplexer. XL is coming here, and the outputs of the flip-flops are being fed to multiplexers also and Q also. And control line is controlling all the multiplexers together. Clear is going to all the flip-flops, clock is going to all the flip-flops. Connections are fine. Let us cross check the simulations as well. We have written the test bench file. So first of all, what we have done is we have declared all the input variables as registers and output as wires. Then we are mapping our register using module instantiation. So the first thing that we do is generate a clock. So we are saying always after a delay of 20 nanosecond, flip the clock value. Then we start our test bench writing. We are mentioning that at t equal to 0, clock is set to 1, clear is 0, XL, which is the input coming for left shift, is 1, XR, which is input for right shift, is 0, and the data which will be loaded at any time is 0011. So we are saying with a delay of 10 nanoseconds, set control to 11. That means we are going to load new data. For 100 nanosecond, it will remain there. And then we are setting control to 01. 01 means left shift. After that, 10 means right shift. And after that, we are holding. Now when we run it, then the results are here. So initially, control was not defined. And here we have declared D from the initial timing. Clear is always set to be 0. Clock is running. XL is 1, XR is 1. So data is undefined till the first rising edge. So here is the first rising edge, and we observe that the control signal is 1, 1. So the data value 3 is loaded. On the next rising edge, it is 3. So we again load the same value. At this rising edge, it is 1. That means left shift. We start shifting left. These two ones will come here, and XL, which is 1, will come on the LSB. So we get 0, 1, 1, 1. At the next rising edge, we are again left shifting. So one more 1 is appended. At the next rising edge, we are again left shifting. So the data remains same. At this rising edge, we are right shifting, and we are inserting a number 0 from the right. So this becomes 0, and then we have one more right shift here. Then it becomes 0, 0, 1, 1. Now here we are just holding for the remaining time period. So this is how we can cross check that how a bidirectional parallel in parallel out shift register can be operated. So students, now we know about the parallel in parallel out shift register. Let us also discuss about serial in parallel out in our next video. Keep learning. Thank you.